let's work on that problem we started talking about yesterday. So here, we have 3 charges. We have charge Q1, start writing again, Q2 and Q3, where 2 of them are positive, 1 of them is negative, and what we want to do is find the total net force, which is acting on the third particle. And as we discussed, what that means then is we're going to use superposition, which says that the total force in this case will be this force, rotated at this particular angle, is then going to be equal to the sum of the forces between the third charge and the first charge, with that as the third charge and the second charge. And just to remind you, Coulomb's law says that the force on the ith particle by the jth particle is equal then to k, where k again is a constant, times the magnitude of the first charge times the magnitude of the second charge, all divided by the distance r squared between the 2. So that's about as far as we got. So I think we talked about yesterday, we want to do this in unit vector notation, but we can do the other one as well, it doesn't matter. We'll do unit vector notation first. So good, so now I have my 3-body diagram, so I know this force is along in 2-dimensional. This force then is in only the 1 dimension, so in y direction. So the total force then will be the vector sum of these 2. So to work on this, we want to write this then into the x components as well as the y components. So in this case, I only have one portion of one force in the x components. And so if this is 30-degree angle here, that means that this angle up here is also 30 degrees. So in the x direction, I only have the x component then of F131. So according to that diagram, would that be the sine portion or the cosine portion in the x direction? Cosine. Cosine portion, good. So this is then going to be equal to F31 cosine of, in this case, 30 degrees, I hats. Back to our picture, we now have all of F32 along the y-axis. We only have this small amount then of F31 in the negative y direction. So in this case, I'm going to have in the y direction, it's going to be plus F32 minus F31. And since this was cosine, this portion has to be the sine portion of it. And it's negative because it's pointing again downward. So F31 is pointing down in this direction. So that's in the negative y direction. This one's in the positive y direction. So pointing along the direction of the positive y. Okay. So this is our force then. So we only have one component in the x direction. We have the 2 components then in the y direction. So from here, all we're going to do then is apply Coulomb's law to this. So Coulomb's law says that this guy then is going to be equal to k times the magnitude then of Q3. Right, as a capital Q, way down on the other page. Times the magnitude then of Q1, all divided by the distance between the 2. I'm going to call this the distance R31 squared. Times cosine of 30 degrees, I hats. And then I'm going to have plus, so I'm going to factor some things out here. So I have a K is for both of these 2 terms. I'm going to factor that out. I'm also going to have a Q3 from here and a Q3 from here. So I'm going to factor those out as well. I'm going to get a magnitude of Q3 times, so then I get a magnitude of Q2 divided by the distance R32 squared minus magnitude of Q1 divided by the distance of R31 squared, all times sine of 30 degrees in the j hat direction. Okay with this? So again here, according to Coulomb's law, both of these 2 terms have a k, so I'm just factoring out that k. This one has a Q3, this one also has Q3, so I'm just factoring out those Q3s. So I don't have to multiply it more than once because there's 2 ways to do things like that. Okay, so what are these different distances? Well, this distance here then is the distance from the first particle to the third particle. So this is going to be our distance of R31, so that's going to be 60 centimeters. And then this distance here, the 30 centimeters, is going to be the R32, since that's the distance from the third to the second. So our 30 degrees in this case will be R32. So from here, we would just plug in all our numbers. In this case, what we find is that this works out to be 120 newtons in the I hat direction plus 260 newtons in the j direction. So after plugging in all my numbers. So this is the net force on F3. Now again, from here, if I wanted to, instead of writing it in unit vector notation, if I wanted to put this into a magnitude and angle, I can do that from here. From here, I can simply say that, well, F3 magnitude is equal to the square root of the x portion plus the y portion squared, square rooted. So if I did that, I would plug in my numbers and I find that this works out to be 290 newtons. That's the magnitude of the vector. And then the angle theta 3. So if I go back to my picture from here, theta 3 then is going to be what? The arc tangent of the opposite side, which is the y portion, divided by the adjacent side, which is the cosine portion, or the x portion. So this works out then to be the arc tangent of f3y divided by f3x. It's mostly on there. Like my numbers, what I find in this case, then it's going to be an angle of about 65 degrees. So that's f3y divided by f3x. It's going to be 65 degrees. And as always, when we talk about vectors, when we go back to what we did last semester, I should always make sure that that vector or that angle makes sense according to my diagram. So according to my diagram, it does make sense because this is 0 degrees, this is 90 degrees, it has to be somewhere between 0 and 90. 65 is in fact, last time I checked, between 0 and 90. So that angle makes sense. Nice. Okay. Let's do another example. So the next example says that we have two charged particles that are both fixed along the x-axis, where the first charged particle, which is at the origin, has a charge of 8q, whatever q is, just some number. And the second charge, which has a charge of -3q, so again, that same q, but it's located at a distance of L to the right of the origin. So let's draw our picture here real quick. So this is our example number 2. So again, here is my x-axis. Here is my y-axis. So it's telling me here, this is my first charged particle. Here is my second charged particle. These guys are separated by a distance of L. And I know that what's Q1, which was this one, is a charge of 8Q. And then Q2 over here is negative, which is then negative, is it 3 or 5?
Negative 3.
Thank you. Times Q. So this is my picture. So then the problem goes on to say, what we want to do now is take a third particle, which initially comes from infinity, which means that the force between the particles is equal to 0, because if I have 1/infinity squared, that's just 0. So taking it from infinity. And I want to bring that guy all the way in and place it somewhere along the x-axis such that the total force is 0 on that particle. So that particle is going to be placed into equilibrium, and the charge on that guy is simply equal to 5 times q. So again, let's put that into our picture. So basically I have some other particle way out here, which is q3, which is equal to 5 times q, and I want to bring that guy in and place it somewhere along the x-axis so that it is in equilibrium. So basically meaning that the force on this third particle must be equal to 0. So this is what I wanted. So the total force between Q1 and Q3 and Q2 and Q3 is equal to 0. So let's do this problem. So the easiest way to think about this problem is to first think of our space into 3 separate regions. So anywhere which is left from charge Q1, in between Q1 and Q2, and then anywhere to the right of Q2. And our first thing we have to decide then is where is it along the x-axis, meaning in region 1, region 2, or region 3, could I put that charge such that the net force acting on it is equal to 0? Because I can't just arbitrarily throw it in there, because at some points it's going to have an acceleration, some points it could actually be equal to 0. So the first thing we need to establish is where could I put it in region 1, could I put it in region 2, or could I put it in region 3, so that it would have a net force equal to 0. So basically all we're going to do is we're going to pretend or look and think, if I put Q3 in region 1, could it have possibly a net force equal to 0? And we'll systematically go through basically each one of these different regions and find the region where it could actually possibly go. Right? So first, let's look at region 1. Could I put this charged particle, for example, here? Could I dump Q3 here? What do you think? So could I dump Q3 there and have it such that it has a total net force equal to 0? Is this a possibility? No, good. Is it just because of the way I asked the question? No, good. Tell me why.
Because they're repulsive forces with nothing acting in the other direction.
Good. So I get a repulsive force between Q1 and Q3. But what about the force between Q3 and Q2?
Q2 is too weak to act over the Q.
Good. So what's happening here is I get a repulsive force between Q1 and Q3. I get an attractive force between Q2 and Q3. But as Derek said, the problem is the repulsive force here is much, much stronger than the attractive force between Q3 and Q2. So overall, the repulsive force is going to dominate and it's going to accelerate in the negative x direction. Why is that? So keep going. You're absolutely right. So tell me why.
Because it's closer to the 8Q. And push it away more than the attractive force can pull it in, so it'll keep accelerating itself.
Absolutely correct. So if we go back to our structure of Coulomb's law says it's dependent on two things. The numerator depends on the sizes of the charges, and the denominator depends on the distance it is away. Which means that, if we go back to our picture, here I have an 8, here I have a 5, here I have a 3, and here I have a 5. Which means that in this case, the numerator is bigger. Right? So I have an 8 times a 5 versus a 3 times a 5, which means that the numerator is bigger. But also this distance here is much, much smaller than this distance here, which means I have a 1 over a small distance squared. Well, what happens if I take a 1 over a small distance squared? It becomes even bigger, right? So basically what's happening in this case is since I have a large denominator and large numerator and a small denominator, that number is going to be huge. Versus in this case, I have a small numerator with a large denominator, which means that that number is going to be very, very small. So what happens in this case is if I try to put it here, this force will dominate over this force, which means overall it's going to be accelerated in the negative x direction. So the answer to this is no. I cannot put this guy in region number 1 because the force to the left will dominate over the force to the right, which means there's no possibility it can sit there at rest. Not going to happen. What about region 2? Could I put my charged particle in region 2? Good. No. Why?
Because it's going to be like repelled by the 8, like to the right, and then it's going to be attracted also to the right. So that's never going to equal 0.
Exactly. Both forces are to the right, right? So if I put this Q3 here, so if this is Q3, as we were saying, I'm going to have repulsive force between 3 and 1. So this is going to be the direction of F3, 1. But at the same time, it's going to be attracted to F2. So I'm also going to get F3, 2 also to the right, which means I have nothing pulling it back to the left. So overall, the acceleration is going to be the right, and it's simply going to accelerate until it slams into Q2. So the answer to this is also no. I cannot put my charged particle in region 2. By default, that leaves us region 3. But let's think about region 3. Could I put it in region 3, say here, and successfully get 0? Go. Yes. Why in this case? Well, now again, I have a large numerator from an 8 and a 5, versus here I have a small numerator from a 5 and a 3. But now this distance here is much bigger than this distance here. So for this one, even though I have a smaller denominator, I also have smaller numerator. I also have a smaller denominator, where here I have a large numerator, but I have a large denominator as well, which means that I can find a location where those two ratios are exactly the same. So the other thing about in terms of forces, I'm getting repulsive force between 1 and 3 again. But I'm getting an attractive force between 3 and 2, which means my two forces are in opposite directions, and I can establish when the two ratios are exactly the same, which would give me exactly a location that I could get 0. So the only place I could put this thing is in Q3, or the region 3. That's it. This is the only location I can put it. Kind of. I could also put it at spatial infinity away, but that's cheap. So we're not going to do that. So technically, I could put it at spatial infinity away, but this is the only place along the x-axis I could actually put it. So from there, using my free body diagram and it's drew here, What that means is we're gonna have F31 to the right minus an F32 to the left. And this has to then be equal to 0. So let's also call the distance from the origin to the location of Q3 as some distance x. So it's gonna be my distance x, and x is what we're gonna be solving for. So good. So from here, we can establish then is that F31 then must be equal to F32. And now let's use Coulomb's law. So Coulomb's law says that F31 is equal to K times the magnitude of Q3 times the magnitude of Q1, all divided by the distance between 1 and 3. Well, that's what we just simply call x. So it's divided then by that distance x squared. That's then equal to F32, which is equal to K times the magnitude of Q3 times the magnitude of Q2 divided by the distance between the two. So the distance between these two is actually this little distance here. So this is the little distance between 3 and 2. To find that distance, well, I know this distance is x. I know this distance is L, which means this little distance is how much? X minus L. So this is now going to be divided by x minus L squared. Okay? Now from here, the k's are the same, let's get rid of the k's. The Q3s are the same, so I get rid of the Q3s. So this thing simplifies then to Q1 divided by x squared is then equal to Q2 magnitude divided by x minus L squared. Now from here, there's two ways we can solve this problem. We could square this thing out, multiply, write it in terms of a quadratic equation, and then solve a quadratic and blah, 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 and that's just no fun. The other way I could do it is I could realize, well, what happens if I take a square root of this side and I take a square root of this side? What happens? I get rid of the squares. If I get rid of the squares, do I have to solve a quadratic? No, so let's do that. Let's be lazy. So let's do a square root on each side. So I do that, and I now have the square root of the magnitude of Q1 divided by x, then is equal to the square root of the magnitude of Q2 divided by x minus L. From here, I'm simply going to solve for x. So let's cross multiply. So this is now going to give me the square root of magnitude of Q1 times x minus the square root of the magnitude of Q1 times L is then equal to the square root of the magnitude of Q2 all times x. Finally, when I want an x, so I'm going to add this term to this side, subtract this term to this side, and factor out the x, and then solve for x. So I finally get that x then is equal to the square root of the magnitude of Q1 divided by the square root of the magnitude of Q1 minus the square root of the magnitude of Q2 all times L. Okay. From here, what I know is that what Q1 is 8 times Q. Q2 is simply 3 times Q when I took the absolute values, which means all the Q's are going to cancel, so I don't care what Q happens to be. I only care about what the free factor is, so this is square root of 8 divided by square root of 8 minus the square root of 3. Plug in all that stuff, what I finally find is that this works out to be, right over here, about 2.58 times 10. So this is the location I would put in. I put them at roughly about 2.6 times L away from the origin. That'd be the location where the force is equal to 0. Now let's make some other comments about this. So the first comment I'm going to make is, what happens if Q3, instead of being a positive 5Q, what happens if it was actually negative 5Q? What would be different in this case?
Nothing.
Ultimately nothing. The only thing that would be different is the directions of these forces would flop. Okay? Because now if this guy was negative, I get a repulsive force between 3 and 2, which means that force would be in this direction. And I now get an attractive force between 3 and 1, which means the force would be in this direction. But ultimately it doesn't change anything. It only changes the directions of forces, but it doesn't change location. Which means that this statement that we just wrote down here is true, regardless if Q3 is positive or negative. It's exactly the same location. Physics-wise, the forces switch direction, but it doesn't change it mathematically. What would happen if instead of this being 5Q, if this was 10Q? Also nothing. The only thing that would happen is the numerators would become bigger, but I'm canceling out Q3 anyways because Q3 is multiplied on both sides, which means it's completely independent of Q3. Which means that the location only depends on these two, it doesn't depend on this one. Which means that it's absolutely independent of Q3, whether Q3 is positive or negative, or the size of the numerator, whether it is 1, 2, 3, 100, or a million, or infinite, the solution stays exactly the same. Now, conceptually wise, it would be a little bit different if I had an infinite amount of charge because it would put a force onto these guys and move that charge configuration. Which means the answer actually would end up being different because I can't keep those charges stationary. But as long as I can keep those charges stationary, the answer is completely irrelevant as far as Q3 is concerned. The answer stays exactly the same. It's fully independent of Q3. Okay? Let's do another. The next example says, when I have 3 charges, 2 of them are positive charges which both have the same amount of charge, capital Q, and I'm going to fix them rigidly to the x-axis where one is at a distance d away from the origin and the other one is at a distance of negative d away from the origin. So let's start drawing our example number 3. So here is my x-axis. Here is my origin. And I'm going to put 2 charges. So I have one charge here, which is capital Q, where this is the distance of d. Go to another one here, which is also the same charge, capital Q. I'm going to put it at a distance of d away from the origin. Okay, so they're both equidistant away from the origin. Now the problem goes on to say, I'm going to take a 3rd charge, which has a charge of Q and a mass of M, so little q in this case, and I'm going to find it to move only along the x-axis. I'm going to put it at the origin, but then I'm going to displacement a small distance in one direction. And then let it go. And we want to know what happens. So let's draw the picture. So I'm going to take my small other particle, draw it here. This is Q. And I'm going to move it a little tiny distance here. We call that the distance x. But we're told that x here is much, much less than d. This will be important. So I'm going to move it. I'm going to displace it to the side. And then I'm going to let it go and we're going to watch what happens. So what happens? So let's talk about the motion before we actually do it. So what's going to happen to this little particle of Q? Good. It's going to get pushed to the left in this case, because what's happening now is since it's closer to this charge, it's going to feel a greater force in this direction than it does from this one, even though it's feeling 2 repulsive forces. But this repulsive force will be bigger than this repulsive force because it's closer. As it moves and gets to the center, what happens to the net force? It's going to go to 0 because now the 2 forces are opposite from each other, but they're equal in magnitude because the distances are the same. And then as it starts to go into this direction, what happens to it? It's going to be pushed in that direction because now this repulsive force becomes greater than this repulsive force, which means eventually it's going to stop, turn around, and then do it all over again. Which means, what's going to be the motion of the particle? It's going to be onto harmonic oscillation, our favorite thing. So ultimately, this thing is going to simply harmonically oscillate back and forth between these 2 positions. What I want to know then is, going back to my question, what's the period? What is the period of this simple harmonic oscillation? And then finally, I'm going to take that all Q's are equal. So this is an iodized sodium atom where all of these particles are simply electrons. And that the spacing is equal to what? 3 angstroms. So 10 to the minus 10 meters is what we call an angstrom, which is the typical size of spacing in a solid. And then find the period in what's called picoseconds. So here we just have to look up at the mass of an iodized atom. Not worry too much about that. Let's plug in that number after. So basically what's going to happen is, again, this thing is going to harmonically oscillate back and forth. And what we want to know then is what is the period of harmonic oscillation? So let's draw our free body diagram. Let's start off with a free body diagram. So here's my little Q. We know it's displaced from its equilibrium position by an amount of x. So this is my amount x. So for now, I'm going to call this, put some subscripts on here. I'm going to call this Q left and I'm going to call this Q right, just so we know which one the force is coming from. Just so we can keep track. So again, what's going to happen is the force between Q and Q right is going to point in this direction because it's going to be a repulsive force. So this one's going to point this way. So I'm going to have the force on, let's call that force right, even though it's pointing to the left, but it's from the Q right. This one is also going to cause a repulsive force in this direction. So it's going to be Q left is going to point in this direction, but the magnitude won't be as big because it's further away. So at the same time, I'm going to get the force in this direction. Let's call that force left. So let's call this our positive x direction. And then I'm going to say the acceleration is going to be in this direction, even though we know it's in the opposite direction. Just so I get that negative sign. So Newton's second law then says that what? The sum of the forces in the x direction must be equal then to the mass times the acceleration, which is then going to be equal to what? F left minus then F right must then be equal to the mass times the acceleration. Now, let's apply Coulomb's law. So Coulomb's law now says that the mass times the acceleration is equal to, so let's go back. So F left is going to be what? K times Q left times Q. So let's put that in. That's the numerator portion. So it's K times Q divided by the distance between the two. So the distance between the two is the distance from here to here. So this is the distance of D, and this is our distance of little x. Then this total distance between the two is what? D plus x. So it's going to be divided by D plus x quantity squared. Minus the force from the left. So it's going to be KQQ again, divided by the distance between those two. Distance between those two is this distance. But again, if I know this distance is D, this distance is x, then this total distance is D minus x. This is then going to be D minus x quantity squared. It's okay? So now what we know is that K, Q, Q are all constants, so let's factor those out. So it's going to be K, Q, Q times 1 over D plus x quantity squared minus 1 over D minus x quantity squared. Now from here, I want to combine these together, so I'm going to find a common denominator. Common denominator is simply a product of these two. So let's do that. So this is then going to be equal to, right over to a little bit, KQQ times, so I'm going to get a D minus x squared minus a D plus x squared, all divided by D minus x squared times D plus x squared. Okay? Now from here, I would square out these terms. What happens when I square these terms? So let's look at each term individually and let's see what happens. So if I do D minus x quantity squared, that's going to be the same thing then as what? D squared plus x squared minus the cross term, which is 2 times D times x. Now if I take D plus x and I square it, that's then going to be D squared plus x squared. And then the cross term is going to be the same, except it's going to come in with a positive sign instead of a negative sign. Okay? So now if I take this term here and I subtract this term from it, what's going to happen? Well, the D squareds are going to cancel. The x squareds are going to cancel. But now this term is going to become negative, so I'm not going to get 2 of these terms, which means I get a negative 4 times D times x. So let's write all that down. So finally, we're going to get MA is then equal to negative 4 times K times Q times D, all times x, divided by D plus x quantity squared times D minus x quantity squared. We're almost there. So now we want to use the condition in the problem, where the condition in the problem says that we want to displace it such that x is much, much less than d. So basically that implies then, let's look at the denominator. Now, if x is much, much less than d, that means this is a ridiculously small term, and this is also a ridiculously small term on those. Which means at this stage, we have two options to take. We can either one, say if I have a ridiculously small term in the denominator, I can always do what my favorite thing in Calc 2 is. What's everybody's favorite thing in Calc 2? Who's taking Calc 2?
What's that equal?
Not set it equal to 0. We're going to kind of do that in a second, but what do you usually do in Calc 2 if you have a really small number? You Taylor series expand it, right? So we could Taylor series expand this term. So in this case, we can do a Taylor series expansion here and Taylor series expansion here, collect all terms together, and then take the lowest order term. Or we could do what somebody said and just take it equal to 0. Okay? Because if x is much, much less than d, if I simply add a ridiculously small number to a ridiculously huge number, what do I get? The ridiculously huge number, right? So if I take 100,000 plus 0.1, what's 100,000 plus 0.1? Technically 100,000.1, but that's approximately just equal to 100,000. By adding 0.1 to 100,000, I didn't really do anything to 100,000. Or if I take 100,000 minus 0.1, that's still ridiculously close to 100,000, so I'm just going to call it 100,000. Which basically means that this thing is going to be approximately then equal to negative 4k QD x divided simply by d to the 4th. So all I'm saying here is that I'm going to treat this as 0, treat this as 0, so this becomes a d squared times a d squared, but a d squared times a d squared is simply a d to the 4th. Okay? Now, I have a d in the numerator and a d in the denominator, so I'm going to cancel out one of those. So this is now going to become equal to negative 4kq divided by d cubed times x. But as we know from being good physics students last exam, to find the angular frequency, all I have to do now is divide by the mass, and then whatever shows up between the negative sign and the x is the angular frequency squared by definition. So let's do that here. So finally, let's divide by the mass. So this is that a then is equal to negative 4kqq over m times d squared times x, which then tells me that omega is equal to the square root of 4 times k times q, all divided by m d cubed. This is my angular frequency. What's up? I wrote it as a square, but it's supposed to be cubed here, and yeah. I tried to fix it without getting it. You're pointing at me. Oh, you're fine here. We like to pretend we're infallible with that. Good, okay? So finally, what I want is the period. What's up there?
Why can't you just get rid of the negative?
Well, we did get rid of the negative, but remember the way we wrote before, as we said, is this goes as a equals negative omega squared times x. So basically, I just want to keep that negative in there to point out that it is actually simple harmonic oscillation. So, yeah. But ultimately, you're right. We get rid of the negative sign when it goes into the angular frequency. So we don't include that portion. So finally, what I want is the period. So I just have to remember that, going back to simple harmonic oscillation, the period is related to the angular frequency by 2 pi, which means this is going to be equal then to 2 pi times the square root of the mass times d cubed divided by 4 times k times q times t. This is my period. Okay. So finally, for the last part, technically part C, we then want to take that what big Q is equal to little q, which is equal to E. We're going to take that the mass is equal to the sodium atom. Of course, I didn't write down, but anyways, we're just going to take those, put those numbers into here, where again, D is equal to 3 times 10 to the minus 10, according to our problem. K is just a number, so again, it's 9 times 10 to the 9th. Plug all that in, and in this case, we find that our period works out to be about 0.24 picoseconds. So here we're just plugging in numbers into our expression. Everyone know what pico is? Small. Small. Anyway, it's negative something. So this is 0.24 times 10 to the minus. Close, that's nano. 12. Minus 12 seconds. So this is a pico. So pico is minus 12. Femto is minus 15. Nano is minus 9. Micro is minus 6. Milli is minus 3. And then there's more than that, but we just know. Okay. So the big point to get out of this problem is simple harmonic oscillation never goes away just because we had a test on it. Be happy. Let's do another one. Great. The next one says. So this says we have a charge Q on a sphere, and a fraction of that charge, let's call that alpha, is going to be transferred to a second sphere, which is nearby. Okay. So let's kind of draw the picture and explain what's happening. So initially, I'm starting off with a sphere, which has a total charge of Q, where another sphere next to it has 0 amount of charge. Okay. Then what I'm going to do is I'm going to touch these two spheres together and transfer some charge between the two via conduction, so that now the entire thing shares the same amount of charge as Q. So the whole thing has Q. Then I'm going to pull them apart. I'm pulling them apart. Here's my pulling apart. And what happens is some of the charge of this one gets transferred to this one, and amount of it alpha, which basically means that this one is now going to have alpha times Q worth of charge, or this one is going to have 1 minus alpha times Q worth of charge. So I'm taking alpha Q away from this one and putting it on this one. So this is what we're physically doing. Okay? Go back to our question. So it wants to know what values of alpha maximizes the magnitude of the force of the electric force between the two spheres. So in this case, I want to know, for part A, I want to know what is the maximum values for alpha, which maximizes the force. So what I want in this case is that explicitly the force is equal to a maximum. Okay, so this is part A. Part B then says, what are the smaller and larger values of alpha that puts the force at actually half the maximum magnitude? So basically, I'm just going to call that part B. So part B, what I want to know is what is alpha equal to if the actual force is equal to half of that maximum force? So this is what we want to know. So we want to say that the force between these two spheres is actually half of the maximum. So what values of alpha, i.e. how much of that charge can I allow to go from one to the other one, so that the total force is actually half of this maximum. So let's do this. So first, let's go back to our picture. So here what I know is what? It says that I have small enough spheres here that I'm going to treat them simply as point particles. Okay, so I'm going to use simply Coulomb form. So now what I know is that this guy here is going to apply a force to him. This one simultaneously is going to apply a force to him. But since I have a positive Q here, say, this is also going to be positive Q, which means this is going to result in two repulsive forces. So what's going to happen then is this one's going to be repulsed in this direction. It's going to be the force, let's call this 1 and this 2. So it's either the force on 1 by 2. This one's going to be repulsed in this direction, so this is going to be the force by 2 by 1. Now, one thing we didn't talk about yesterday, which I'm going to talk about now, is the fact that Coulomb's law actually satisfies Newton's third law, which means that the force on this guy is exactly equal to the force on this guy, just in opposite directions. So this satisfies completely Newton's third law, which means this force here has exactly the same magnitude of force on here. So whichever force I decide to use, whether it's this force or this force, will give me the same answer. It doesn't matter which one. The only thing that's different is the direction. So what I want to do then is what? Maximize this or maximize this in respect to alpha. But again, whichever one I choose, it doesn't matter, because the size of the forces are going to be the same. So let's go ahead and do that. So which one do you want to work with? F12 or F2? F21, great. So let's look at F21 first. So let's look at part A. So let's say we want F21. So here's my force F21, magnitude. So it's going to be K times the charge Q2, which was alpha times Q. So that's my charge Q2, times Q1, which is alpha minus 1 times Q, all divided by the distance between the two. And I'm simply going to call that distance D. I'm going to say this center to center distance here is simply now, what I want to do is maximize this force in respect to alpha, right? Which means that in calculus, got 1 at the stage. How do you extremize a function?
Maximum.
Look for the maximum, the local maximum, local minimum. Good. And how do you do that? Take its first derivative and then do what? And then do what? Solve for the thing that you're maximizing. Exactly. So here, since we want to maximize this guy in respect to alpha, what that means then is we have to take the derivative of this with respect to alpha and then solve for alpha. That's how we maximize a function. So in this case, we want to consider then the derivative of F21 with respect to alpha, set that guy equal to 0, and then solve for alpha. So that's equivalent then to the derivative of K alpha minus 1 times Q squared, all divided by the distance B squared. This is what our job is. Our job is now to extremize this and then determine exactly what the value of alpha has to be. Okay. Now let's look at what we have. Does K depend on alpha? Does Q depend on alpha? Does D depend on alpha? So K, Q, and D are all constants as far as alpha is concerned, which means I can factor them outside of the derivative because they give me nothing. So this is going to be the same thing then as K times Q squared divided by D squared, all times the derivative with respect to alpha of alpha times alpha minus 1. What's up, Omar?
Why is it alpha minus 1 and not 1 minus alpha?
Oh, sorry, you're right. 1 minus alpha. Because I had a little dyslexia in there. Now, since all this is equal to 0, does it depend on any of the square? No. So I can divide all that out. That's I'm going to change my answer. So I'm just going to divide all this out, which means I'm finally left with that 0 then is equal to the derivative with respect to alpha of then what's alpha squared minus alpha. What's the derivative of alpha squared with respect to alpha?
Isn't that alpha minus alpha squared?
I did it again, didn't I? Thanks, Eric. Good. So what's the derivative of alpha with respect to alpha?
1 minus 2 alpha.
Good. So 1 minus 2 alpha. So it's going to be equal to 1 minus 2 times alpha. And in this case, we're specifically looking at alpha max. Good. So if I multiply this out or solve for alpha, this tells me that the maximum value of alpha is then going to be equal to simply a half. So the amount of charge, which I would transfer from one sphere to the other sphere, which would give me the maximum amount of force, is half the charge. So that's what this thing is saying. So to maximize the force between the two spheres, I want to give each one exactly the half of the amount of charge that the other one started off with, which would then extremize the amount of force between the two. Is that a question, Omar?
Yeah. How'd you figure out to multiply the one which is 1 minus alpha?
Oh, because, so let's go back to our picture here. So again, if I start off with Q here, but then I move alpha Q to this one, so how much do I have remaining?
How much you subtract?
Exactly. So I have whatever I started off with minus the amount of which I took away. Right. So that's what this is saying. So this is saying I started off with Q, but then I'm subtracting the amount that I moved over here, which is alpha Q, and then I subtracted out the Q. So it's going to be 1 minus alpha up there. Okay. So all this is if I want the biggest amount of force between these two, I have to take half of this one away, put it here, so this has half remaining, and this has half. That extremizes the amount of force. So what's the maximum amount of force then? Well, the maximum amount of force then is just going to be F21 evaluated at alpha max. This will be my maximum amount of force. So let's do that, because I need F in the next one. So F max then is going to be equal to F21 evaluated at alpha is equal to alpha max. This is going to be my maximum force. So let's plug that in. So it's going to be what? K times Q squared times alpha max times 1 minus alpha max, all divided by the distance d squared. So this is going to be equal then to K times Q squared times a half, all divided by d squared. It's going to be the same thing then as KQ squared divided by 4 times d squared. So this is my maximum amount of force. My maximum. Okay. So finally, part B and C, but B together now says, well, what we really want is that the force F21 is equal to half of the maximum force. And we now know the maximum force then is equal to what? K Q squared over 4 times D squared, which means the force that we want is going to be 1/8 of KQ squared over 4D squared. So now what I want to know is what is alpha equal to make this statement true?
Why is it 1/8?
What's that?
Why is it 1/8?
Because I'm taking 1/2 of the 4. So I have the 1/4 down here. So I'm just factoring out the 1/4. Oh, sorry. I see what you mean. That should just be a D squared. Good. Sorry about that. So I moved the 4 out front to make it a 1 times 2, and then I left the 4 there. So sorry about that. But at the same time, we know F21 from our previous part is going to be equal to K times Q squared divided by the distance D squared times alpha times 1 minus alpha. So F21 still has to be this value, but I want that equal to 1/2 of the maximum force, where the maximum force is this guy. Now again, the K's are the same, so I can cancel out the K's. The Q's are the same, so I can cancel out the Q squareds. The D's are the same, so I can cancel out the D squareds, which means I'm finally left with alpha minus alpha squared then is equal to 1/8. This is a quadratic, which means there are going to be 2 solutions. Here I just have to solve the quadratic. The lower solution is going to be part B. The higher solution then is going to be part C. While we're doing from here. So let's rewrite it in terms of a quadratic. So it's going to be then alpha squared minus alpha plus 1/8 is equal to 0. So now I just simply have to solve this for alpha. Okay. This tells me that alpha then is equal to negative b, where negative b is simply 1, plus or minus the square root of b squared, which is 1 squared, minus 4 times a, where a is also 1, times c, which is 1/8, all divided by twice of a, where twice of a is 2. So this is then equal to 1 plus or minus the square root of 1 minus 1/2 divided by 2. What's 1 minus 1/2? 1/2. So finally, this is equal to 1 plus or minus the square root of 1/2, all divided by 2. So this means that for the higher value, I'm going to keep a plus sign. For the lower value, I'm going to keep the negative sign. Okay. I'm just going to leave it that way. What's up, Omar?
We can go back.
Sure.
Wait, so how did you know about those 2 expressions?
Oh, because here I'm saying I simply have F21. And this is what we wrote down initially for what F21 is. But the parameters of the question is that I want F21 explicitly to be equal to half the maximum amount of force.
Oh, okay.
So this was the parameter of the question itself. So again, if I go back to my question, that's what it says here. So the magnitude of the force is, oh, there it is. So what values of alpha that put the force at half of the maximum magnitude? So I just want F21 that is equal to half that maximum. So that's what the parameter of the question was asking. So doing that, then that tells me that, again, the F21 has to equal to that, and then I can solve for the alpha values. Okay. So tomorrow, we'll start talking about electric fields. So what is an electric field? What is it actually? And all kinds of interesting cool stuff with electric fields. Don't look like I slapped you with calculus. Okay. I'll see everybody tomorrow. Have a good rest of your day. Want to see math the rest of the day.